Can you hear me, guys? All right. Now, regarding the question about the Wednesday, yes, we will have another lecture actually on Wednesday. But now, let us finish our lecture for today. Today, we are going to talk about chapter 7, which is in edition 9. So, edition 9, it's chapter 7. And it will be actually the second part, because the first part, what we have discussed previously in the chapter of the alkene, we have discussed the IPAC nomenclature and the degree of unsaturation. So we are not going to study or re-discuss these aspects because we have already discussed them. So please refer back or go back to the previous lecture where you have to find the IPAC nomenclature of alkene and how to calculate the degree of unsaturation. In principle, for the nomenclature of alkene, as we have explained before, we have to find the longest continuous chain of carbon atoms which contains both of the carbons, making the double bond, and then we have to replace the final ane in the corresponding alkane with ene. Then we have to designate the location of the double bond by the shortest number, and then we have to simply to try to give the other substituent the lowest possible number. But of course, since this alkene is a functional group, then the priority for numbering will be definitely goes for the alkene. I hope you just go back to the previous lecture where we have studied the nomenclature of the alkene and then study them carefully. Now, we have discussed previously some properties about carbon double bond carbon, and we said around carbon double bond carbon rotation, and because simply, as I said before, as we explained, the carbon double bond carbon contains the pi bond, and you can see the pi bond, it's simply the interaction of the two parallel p orbitals. If there will be free rotation, that means these p orbitals will go away from each other, and therefore, which means the bond will break up. And that's actually always, as we said, bond making is a favorable process, while bond breaking is definitely not a favorable process. Okay, Aisha, I will record the meeting now. All right, so this is a very important aspect that in the chapter of the alkene we said around carbon-carbon sigma bond, free rotation is allowed, and that's why we do have this will make what we call them conformational structures, and we said we do have the eclipsed and staggered conformation. But around carbon double bond carbon, there is no free rotation. And that's why we will have actually a new situation where we have something called cis and trans isomerism. And that's actually what we are going to discuss today or now. The cis and trans, we use this cis and trans word to indicate the orientation of the groups to each other around the carbon double bond carbon. So if we have two groups, suppose A, B, around carbon double bond carbon, in this case, because the free rotation is not allowed, this compound will differ than this compound, where we have the A and B are in the same phase. In the first compound here, we have A in opposite or in different phase or plane compared to the second compound, where we have A and B are in the same plane. So in this case, the first compound here, we give it the name trans in order to distinguish it from the other compound, while the second compound here, we give it trans. This is trans, and this is, we give it the notation cis. and then it will be the same name, identical name of both. So the cis and trans actually, they are stereoisomers, and we must differentiate them by adding cis or trans. Now again here, the trans means two groups are in opposite or different planes or phases. While cis means the two groups, everything is the same, but the two groups are in the same plane. Do you follow me, guys? So this is trans because the two groups are in opposite planes or opposite phases, while here the cis, the two groups here are in the same phase or plane. Is there any question about the cis and trans? Perfect. So that's always the case. And by the way, as we said, for example, let's take typical. Yes, please. Now, let's take typical example and see the name of the two compounds. For example, this compound, a compound like this, and let's give the name of these two compounds. As you can see, first of all, I think when you apply the APAC rules, would be straightforward. We should know that the longest continuous chain of carbon atoms, in this case, which contains both of the carbons, will be 5 carbons. So it will be, the name of this compound will be 1, 2, 3, 4, 5. So that means 2-pentene. And this is the same, will be 2-pentene. Now, the difference between this and this, these are two isomers, these are two stereoisomers. The difference is that two groups in here are in opposite directions or in opposite planes. Therefore, we must distinguish this from the first one, and that's why we add trans. While in this compound, we have the two groups, they are 1, 2, 3, 4, 5. Yeah. These two groups are in the same plane or phase, and that's why we must add cis. So the name of the first compound will be trans 2-pentene, while the second will be cis 2-pentene. Now, what's the relationship? If I ask you, what's the relationship between these two structures? They are stereoisomers, but these two compounds, they are not mirror images to each other, and therefore they must be diastereomers. Diastereomers. Remember, any cis-trans isomerism is diastereomers. Always true. Any cis-trans diastereomerism or diastereomer, a relationship cis-trans, that means they are diastereomers. Do you follow me? Is there any questions so far? Write down or speak up. Is there any question?
No.
Sure. All right. Now, in this case here, as you can see, now you have to remember that if we have two alkyl groups attached, or two groups attached at the same carbon of the carbon, the bond carbon, there will be no cis-trans. In other words, if you have here CH3, double bond C, CH2, CH3, and then hydrogen. Now the question is, if we draw them in different ways here, CH3, CH3, and then here the hydrogen, and then here we have CH2, CH2, CH3. 3. Now, if I ask you, what's the relationship between structure number 1 and structure number 2? Are they stereoisomers? Are they the same compound? What are they? Are they isomers or they are the same compound? What do you think? The relationship between structure number 1
the
and 2.
same compound, I think, Victor.
Why? Why they are the same compound?
Because they are just macrosas.
Yes, exactly. If you flip one of them over, if you just make a rotation by 180 degrees over the plane, you will get the other one. And of course, in your object, if you flip it, if you rotate it, and you got the other one, that means they are the same compound. So these two are the same compound. Now, what I want to say, what I want to highlight, whenever we have two groups, two same groups attached, or two groups are the same, attached to one of the carbons, making the carbon double bond carbon, there is no cis-trans. No cis-trans relationship. Remember that. I'm just giving you some hints and some key in order to be aware of what's going on. So, cis-trans isomerism, if we have two groups attached to the two carbons, in this case, we should expect to have cis-trans. But if we have two identical groups attached to the same carbon, which makes the double carbon, then we should expect that we should have no cis-trans. Right. Let's make. You cannot see what I write? Can you hear me, guys? I don't know why. Is this for all or just some of you? Okay, Khalaf, what should I do if you have a problem in the internet? Now, let me hear from others. Do you hear me well, guys?
Yes, doctor.
Okay, so if someone has a problem, that means you have a problem with the connection. You may simply either try to continue with us or simply look for the lecture, the recorded lecture on the YouTube later on. You follow me? So if some can hear me nicely, that means you have a problem in the internet. Amar, what's the butter like previous lecture? What do you mean by the previous lecture? What do you mean, Omar? It is recorded by another device, Omar. You will see it later on. You will see it when we finish the lecture. Anyway, let's continue now. Now let us see a situation where it's a little bit more sophisticated and we have more groups attached to the carbon double bond carbon system. For example, if we have carbon double bond carbon, here we have methyl, here we have brom, here we have ethyl, and here we have chlorine. You follow me? Now, this compound, first of all, what we call this compound? So if we want to just apply the APAC nomenclature here of the compound, what would be the name of this compound if we want to apply the APAC rules here? What should it be? Anyone? No, I'm talking about APAC name. Just give me the full name of this compound. What should it be? Of course.
2-bromo.
Yes?
2-bromo. 3-chloro.
Right.
Pentene.
Absolutely. 2-bromo, 3-chloro, 2-pentene. It will be 2-bromo, 2-chloro, and then don't forget, we must designate the location of the double bond all the time. So it will be 2-pentene or you may draw it, or you may say 2-bromo. Yes, please, go ahead.
Will be 3-chloro.
Sorry, 3-chloro, you're right. 3-chloro, then pent, then 2-ene. Both are correct. So either this or that are correct name. You follow me? So it will be 2-bromo, 3-chloro, 2-pentene, or we may write it like this. 2-bromo, 3-chloro, pent, without this. Pent, then 2-ene. It's either way is fine. But, so this is the IPAC name. But now we need to know that there is different possibilities. For example, here, I may draw this way. For example, if I have another compound, and this is the structure of this compound. Now we can see the second compound, it's a stereoisomer of the first because it contains the same number of carbons, the same number of hydrogens, the same number of all atoms. So they have the same molecular formula, and they have the same connectivity of atoms, but the only difference is there is only the spatial arrangement of atoms in space. Do you follow me? So these are two stereoisomers. Now, but the question is, what should I use? How can I distinguish the name of the two? Now, whenever we have more than two groups, as you can see here, we have 4 different groups attached to the carbon double bond carbon system. The same thing, of course, in here. In this case, we don't use no longer, or cis-trans isomerism is only used, is good enough for 2 groups attached to the carbon double bond carbon system. But 3 or 4 groups, when we have 3 or 4 groups attached to the carbon double bond carbon system, then we don't use cis-trans, we do use instead Z or E system, where E corresponding to the trans and the cis corresponding to the Z, as we will see it. Do you follow me? We will now see what's the system and how we can use the E and Z system in this case. Do you follow me? But the most important thing, as I said, we do use cis-trans when we have 2 groups attached to the carbon double bond carbon system only. But as in this case, you can see here, how many groups attached to the carbon double bond carbon? We have 4 groups. In this case, we don't use cis-trans system to distinguish the different stereoisomers. We use instead a new system which we call it Z or E. The E is equivalent to the trans, and the Z is equivalent to the cis. It's actually, the Z is coming from a German word called zusammen, which means together, the same plane. While E it's the first letter of a German word called entgegen, which means opposite to each other. So this is together. In other words, we will see how we apply the system, and we'll see the rules for the E and Z system. But the most important thing to remember that the equivalent word to the cis is Z. The equivalent word to the trans is E. Remember that. Do you follow me? So what the cis stands for? Cis stands for 2 things in the same plane. What's the trans stands for? Trans stands for 2 things in opposite planes. Do you follow me? Similarly, the Z stands for 2 things in the same plane, while the E stands for 2 things in opposite planes. Is that clear so far, guys? So far, is that clear? Is there any question about it? Okay, perfect. So let's see now the E and Z system and how we apply it. Just remember this and leave one example, and then we'll come back to the other one. When we want to use E and Z system, first rule, we must assign priority for the groups, for all groups. Do you follow me? Now, assigning priority, it's like the previous chapter, if you remember, in the stereochemistry, we did assign priority based on the atomic number of the directly attached atom. If we cannot find a decision, all right, what should we do? We should simply continue comparing the next attached atoms and the next until we find the difference. Do you follow me? And all the rules applied before what we have discussed in chapter 5, it's the same in here. For example, in here, what we should do, it's very simple. I'm not going to repeat what we have discussed already in chapter 5. We have already discussed in chapter 5 how to assign priority. If you remember, we did assign priority of the 4 groups. All rules we have discussed for assigning priority in chapter 5 applies the same here. You follow me? Now, what should we do? In this case, as you can see here, we have 4 groups attached to the carbon double bond carbon. What should we do? We should simply assign priority here. For these 2 groups attached to this carbon, which one of the 2 groups has higher priority? Do you follow me? As you can see in here, the first atom attached to this carbon is carbon. Here we have bromine. And of course, as you all know, bromine has way much higher atomic number compared to the carbon. So this is the one which has higher priority. I will label it as a star in this case. Do you follow me? Now, when we turn our attention to the 2 other groups attached to the other carbon. Here we have chlorine and the carbon. Again, as you can see here, the chlorine has higher atomic number compared to the carbon. Do you follow me? Now, as you can see here, we have the 2 highest atoms here. We have this highest priority atom. This is the highest priority atom. They are, as you can see, they are in the same plane. Same plane means cis or Z in this case. So we must assign this the Z configuration, and then we continue the full IUPAC name of the compound. Is that clear, guys? Any question about assigning E and Z configuration of the alkenes? If you have any question, please open up your mic and ask.
It's clear, doctor.
I'm sorry? Clear? Perfect. I mean, if you have any question, is there any question, guys? Any other one has any question about it? How to assign E and Z? Again, just to make the story short, all what we need to do, we need to compare the 2 atoms attached to one carbon, one side. And then we must determine which one has higher priority. Higher priority according to what we have studied in chapter 5. In this case, very obvious that this bromine has higher priority than the carbon. So let's label it. Now we turn our attention to the other carbon. Here we have again 2 atoms. If we have chlor, we have carbon. The chlor has higher priority than the carbon. Now when we compare these 2, the higher 2 atomic properties, they lie on the same phase, the same plane. Therefore, we must assign it the Z configuration. While the other one...
Doctor,
Yes, please.
what if we have more than one double bond?
That's a very nice question. That's a perfect question, actually. Then we must do the same for every other carbon double bond carbon. Do you follow me? We can take an example and see it. Alright? Do you follow me?
Okay.
So here, for example, this carbon double bond carbon, we know it is Z. Do you follow me? So for example, if the location, if this carbon double bond carbon is 2, then we specify 2Z. The other double bond, if its location is number 5, then we specify 5E or Z, whatever it is. Let's take a specific example accordingly. But before taking this, before taking more sophisticated example, let me just ask again and highlight on the same issue. I want everyone to understand it. Does anyone have any question about it? How to determine E and Z according to the rules? Is there any question? Wonderful. So everything is clear. Now let's take more, complicated questions. Suppose, for example, C double bond C, CH3, hydrogen, CH2, hydrogen, then, carbon, then hydrogen, then C double bond O, CH3, then here, let's make it CH2, CH3. For example, suppose. Do you follow me? In this case, as you can see, we have two carbon double bond carbon. We have this carbon double bond carbon, we have this carbon double bond carbon. Of course, this is, I just put this example just to give you more practice. But in this case here, the numbering must be started from this direction. We will come to this. When you study organic 2, you will see that this is ketone, and the numbering, we must start numbering from this direction. Anyway, if we start numbering from this direction, it will be 1, 2, 3, 4, 5, 6, 7. So in this case, what you will see, we have carbon double bond carbon, carbon double bond carbon, and their location are 3 and 5. So in this case, we need to specify carbon double bond carbon at the position 3. What's its configuration? Is it E or Z? The same thing we must specify for 5. Let's look for 3. What we have? We have 3 groups. We have this group, we have this group, and you have this group. Do you follow me? We're talking now about the configuration of 3. Of course, very obvious that the hydrogen is the lowest. So this is the higher atomic mass number of the 2. In this case, you must define that this is not the highest priority atom. I'm not gonna discuss it. You can just simply go back to the rules, what we have discussed in chapter 5, and see the priority. So this group has higher priority than this group. You can see here, number 3, these two groups, which are the higher priority, they are opposite planes, which means they are E. So number 3, carbon double bond carbon configuration is E, while number 5, as you can see here, we have this group and that group. They are very obvious that this is Z configuration. So this is how we, and then we continue the full APAC name if we can do it. Do you follow me? Is that clear? Yes, please.
Can you repeat, please?
Okay. What I'm saying, we must determine the configuration of each or around each carbon double bond carbon separately, and then we simply list the configuration of each carbon double bond carbon with its location. So you say here we have 2 carbon double bond carbon system. We have this and that. Is that clear so far? Clear?
Yes.
Okay. Around this carbon double bond carbon, we have 4 groups. We have this group, this group, this group, this group. Now what we said, we need to compare these 2 groups. Very obvious that this group has higher priority compared to the hydrogen. Any atom, it has higher priority compared to any hydrogen. Clear? You follow me?
Yes.
Okay. Now, when we compare these 2 groups, you should find out easily that this group has higher priority than the ether. You know? Do you know why? The one who was asking.
Yes, doctor, because it's attached to 2 carbon and 1 hydrogen.
Exactly, absolutely. When we simply deal with this, when we analyze this, according to the rule, we should discover that this carbon is attached to carbon, carbon, hydrogen, while this here is attached to hydrogen, hydrogen, carbon. That's why. If you, for anyone else who forget, if you forget this rule, please go back to chapter 5 and see how we deal with the priority of the atoms, how we analyze the priority of the atoms. Anyway, so when we done with that, it's obvious now that two priority atoms, they are in opposite directions or in opposite planes. Therefore, the carbon double carbon, which is at position 3, it has a configuration of E configuration. Carbon number 5, or the double bond carbon at position 5, as you can see, we have these two groups, this group and this group, they are in the same direction, therefore we call it Z configuration. Clear?
Yes.
Perfect. Is there any other question regarding the E and Z configuration? Any other question? Let me just give you... Yes, please. Okay, so let me just give you this example. The example which you have it, I don't know what's the page, but you have it in the slides. For example, what's the configuration around this carbon, the bond carbon? Here we have CO2 methyl, and then here we have CO2H, I think, right? Then here we have isopropyl, and then we have here carbon, double bond carbon. Now, as we said, in order to determine the configuration around this carbon, double bond carbon, we need to compare these two groups separately and see and find which one has higher priority. Obviously, this carbon or this group has higher priority than the isopropyl, and I think we have done this. We have worked that before in chapter 5. Similarly here, when you compare, when you keep comparing, this carbon is the same like this carbon. The oxygens are the same, but the oxygen here is attached to carbon, while the oxygen here is attached to hydrogen, and therefore this will be again higher priority. When you compare, now we have two higher priority, they are on the same phase or plane, and therefore this configuration must be the Z configuration, regardless of its APAC name. Is that clear? Is this clear, guys? Hello, is this clear? Okay, perfect. Now let's talk about stability of alkenes, and let's explain the stability of alkenes. Stability of alkenes. Generally speaking, I'm just going to go for the whole comparison. If we have tetra substituted, tetra is more stable than tri, is more stable than di, and the di is more stable than mono, and mono is more stable than non-substituted alkenes. In other words, if we have carbon double bond carbon attached to 4 R groups, where R here is any carbon attached to the system, that's actually what we refer by R. So as you can see here, the carbon double bond carbon is attached to 4 alkyl groups. So that's why we call it tetra substituted. This will be more stable than carbon double bond carbon attached to 3 substituents, where we have one of the substituents is in here, a hydrogen. So this is tetra substituted, tri substituted, I'm sorry. And then we have carbon double bond carbon, double bonded, R. Let me just sort it like this way. It's R, and then hydrogen. This is trans. The trans will be more stable compared to the cis. And then we have the mono substituted, and the cis will be more stable than the carbon double bond carbon RR hydrogen, approximately the same stability, and this will be more stable than if we have only one alkyl groups attached to the system, and that will be more stable if we have all atoms are hydrogens. In other words, just to make the story short, as the number of carbons attached to the carbon double bond carbon system increases, the stability will increase. Do you follow me? We will explain now later why is this, or why this trend is true, but this is simply the summary of the whole issue. As number of carbons attached to the carbon double bond carbon system increases, simply stability will be higher. You can see your check here. The first compound, which is the most stable one, is the tetra substituted, which means we have the carbon double bond carbon system is attached to 4 carbons. The next one is attached to 3 carbons. These 2 or these 3 systems are attached to 2, like with some difference in the stability. For example, the trans, I think it's obvious why the trans is more stable than the cis, because simply the steric hindrance is less in the trans system. All of them are more stable than the monosubstituted, while the monosubstituted is more stable than the not substituted system. Now, let's explain why we have this trend of stability. Why we have, or why this type of stability? Why, as the number of carbon attached to the carbon double bond carbon system increases, the stability increases? So let me just rewrite it down. As number of sp3 carbons, let's make it like that. As number of sp3 carbon atoms attached to carbon double bond carbon system increases, stability increases. Why is that? Due to what we call it, due to hyperconjugation. We'll explain now what is the meaning of hyperconjugation. Do you follow me so far? Do you follow me? As the number of carbon atoms or sp3 carbon atoms attached to the carbon double bond carbon system increases, then the stability of the alkene will increase. And why is that? Due to something called hyperconjugation. What's the hyperconjugation? Hyperconjugation, it's some sort of increasing bonding in the system. What did we say about everything in life? Why any process happens? What's the motivation? What's the attraction? And what's the attraction? It's simply making bonds. Always. Bonds is attraction forces. Do you follow me? So it's the motivation of anything to happen in life is actually to have more attractions, which means more covalent bonds. Covalent bonds are simply more attractions. So hyperconjugation is like increasing the bonding. How it will increase? How the presence of a carbon near carbon double bond carbon system will increase the number of bonding. Simply, let's just rethink of the carbon double bond carbon system. If we have carbon double bond system, carbon double bond carbon, we have the carbon is sp2 hybridized, and if you remember the bonding in the alkene, we said we have on each carbon there is a p orbital, and these p orbitals are parallel to each other, and they make the bond by the side-to-side interaction of the p orbitals. Now, if we have a carbon, which is sp3 hybridized, and there is a hydrogen attached to this carbon, if there is a hydrogen attached to this carbon, so this is attached to a hydrogen, regardless of what the system is, I'm just going to just make this empty like that. You follow me? Now you can see here we have between the carbon and the hydrogen, this is sigma bond made by the sharing of the electron in the s orbital of the hydrogen and the carbon. So here we have 2 electrons in this orbital, in this s orbital. Now here, according to molecular orbital theory, and I hope you will study this actually in more details in general, in inorganic chemistry. Whenever we have, in the molecular orbital theory, whenever we have a bonding orbital, so this is the bonding orbital of the of the pi electrons. So this is called bonding, and this is called anti-bonding. Now the bonding orbitals here simply made by the sharing of the 2 electrons. So we have sharing of the 2 electrons in the p orbitals, we call it bonding. For the system here, carbon double bond carbon. The carbon double, beside this bonding, we have something called anti-bonding, where we have the sign of the p orbitals are opposite here, so we have plus minus, and this is minus plus. Anti-bonding here, this is empty p orbital, while the bonding is full or p orbital. Do you follow me? Now, what's going to happen actually, it's sharing of the 2 electrons in the s, in the sigma bond, with this anti-bonding. This is plus plus, minus minus. So this is called anti-bonding. This anti-bonding is empty, so it can't accept electron. So this 2 electrons as if makes some sort of overlap with the sigma electrons. Remember my words, it's the situation, it's not like typical bond. No, of course not. I mean, this has carbon to hydrogen, its own bond. This carbon double bond carbon system, it is own system. But there is some sort of interaction between the empty p orbital or the empty anti-bonding in the carbon double bond carbon system and the sigma bond. This is here, this is like interaction. This interaction, this is simply more bonding, and which means simply more stability. Do you follow me? Does anyone, or did anyone study inorganic chemistry 1 of you? Did anyone study inorganic chemistry 1? I need answers. Nobody? Maria didn't? Anyone else? Nobody. Okay. Remember that when you study inorganic chemistry, the first thing what you will study in the inorganic chemistry is something called molecular orbital theory. Whenever we make, or according to the molecular orbital theory, whenever 2 orbitals, any 2 orbitals, when they interact, there is 2 ways for this interaction. Either what we call it constructive overlap, or what we call it destructive overlap. The constructive overlap makes what we call it bonding molecular orbital. The destructive overlap makes what we call it anti-bonding molecular orbital. So that's actually the whole case. The hyperconjugation is overlap of sigma electrons between the adjacent carbon-hydrogen system with the anti-bonding of the molecular orbital of the carbon double bond carbon system. So again, just to make the story short, hyperconjugation, I just want to define it in here. Hyperconjugation is overlap of adjacent sigma electrons, let's say adjacent sigma electrons which present in carbon hydrogen with anti molecular orbital of carbon double bond carbon system. That's actually the definition of the hyperconjugation. Let me just a little bit jump to the next step. No, Maria, you are not supposed to simply fully understand the molecular orbital theory now, but I'm just telling you now to make connection when you study an organic chemistry, to connect it with the organic chemistry in a way or another, because actually that will explain this in more details. And even in the organic chemistry too, you will definitely rely on some aspects where we simply explain some aspects by molecular orbital theory. So all what you need to do to know is just hyperconjugation is some sort of more bonding. It's an overlap of the adjacent sigma electrons with the anti-molecular orbital. In order just to make you understand it more, let me just jump a little bit to something else more. Something like this. Imagine we have a carbon, which is, this carbon is positively charged. In this case, what would be the hybridization of this carbon, guys? What will be the hybridization of this carbon if the carbon is positively charged? This answer or this question should take
sp2.
Yes, very fast. sp2 right away. So this is sp2. Of course, we know that carbon in general does not like or does not tolerate to have a positive charge on it. It's simply always, any atom actually prefer to have a neutral. It shouldn't, the charge is not something which is suitable in this case. What does that mean? What does that mean, the sp2? It means the carbon here, it's planar system like this, and every bond here is sp2, 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 and we have a p orbital over the carbon. That's actually why it's sp2. So we have empty p orbital, isn't it? Is that clear, guys? And this empty p orbital, it has the plus. It's vacant p orbital. Has 0 electrons. That's why it's a plus. Isn't it? This is simply the bonding in the sp2. Is that clear so far, guys? Are you with me? Yes, please.
The plus only for the above?
No, of course not. No, of course not. It's because this is p orbital. The p orbital is always above the system and below. So it is, but I don't want to write it twice in order not to make any confusion for some of you to think it's two charges. Do you follow me? Do you follow me? Who's asking?
Yes, yes.
You got it? So it's the plus, it's for both. Here, this p orbital is two loops. It's one loop above the plane, one loop is below the plane, which means these two loops are carrying no electrons, plus there is 0 electrons in there. Got it?
Yes.
Perfect. Now, as we said, a carbon to carry a plus is something, not that much favorable. It's not stable. What other thing can make it stable is the hyperconjugation. For example, if there is a carbon here now, near this carbon, if this carbon is attached to another carbon, while this carbon has a hydrogen, or attached to another hydrogen, for example, you can see here, this is a sigma bond, right? The sigma bond with the adjacent hydrogen, the adjacent carbon. Now, this sigma bond can now hyperconjugate with the vacant p orbital and make some sort of bonding, some sort of stabilization, some sort of attraction. And therefore, this carbon, this charge become, or this carbocation becomes more stable. Do you follow me? Do you follow me, guys? Do you follow me? So this is simply, it's like more clear example of what we mean by hyperconjugation. Hyperconjugation is simply interaction or simply some sort of overlap of adjacent sigma bond with something needing of the electrons. In this case here, very obvious, the p orbital in the sp2 is vacant, has no electrons. It's in desperate need for more electrons. That's why this is some sort of bonding in this case. So that's why actually, by the way, as number of carbon or number of alkyl groups attached to carbocation increases, stability increases. Do you follow me? Due to the hyperconjugation. For example, the first thing what we are going to discuss after this topic, after this section, is the stability of the carbocation. So that's why let me just write it down. Carbocation, if we have a carbocation attached to 3 alkyl groups, this will be very much more stable compared to a carbocation attached to 2, compared to carbocation attached to 1 only, and compared to a methyl carbocation, CH3. That's actually the trend which we are going to discuss it in the next section. So instead of discuss the whole topic twice, it's the same explanation. The explanation is why this trend of the stability is because of the hyperconjugation. Hyperconjugation makes the sigma bond in here overlap with the vacant p orbital on the adjacent carbocation, and thus makes some sort of bonding, and thus makes more stability. Got it, guys? Is there any question? It's okay. That's the most important thing. Is there any question? Are you sure you got it perfectly? The hyperconjugation and stability, because actually it's all are the same. So this is important, extremely important. Please remember this, because when we start discussing the next chapter, the next topic of the chapter, which is the addition reaction to the alkene and the mechanism of the reaction and explanation of what we call it Markovnikov rule, it will be always based on the whole issue in here. So I think I will just use more time, just maybe another 10 minutes, guys. Just bear with me, please, and then we can stop at this point. Let me just discuss. I'm just going to leave what we have discussed so far here. So carbon R, hydrogen, hydrogen plus. It's more stable than carbon, hydrogen, hydrogen, hydrogen plus. This is always stability. Let's talk about addition, reactions of alkenes. In principle, when we discussed the addition reaction, we said addition reactions like two molecules, they add themselves to each other and then to form bigger molecule. So for example, if we have carbon, the bond carbon, we allow it to react with HBr. What we are going to get, the HBr will add itself to this molecule, and then we are going to get addition product. Do you follow me? So this is an example of what we have discussed before, and we called it addition reaction. Now we want to explain a little bit of what we call it the mechanism of this reaction, and we want to explain a very important theory of the addition reaction, what we call it Markovnikov addition rule. Now the mechanism of the reaction. The mechanism, it's very simple actually in this case when we have, it's like acid-base reaction first, where we have the carbon double bond carbon, the bi bond here will be added to make or will be used to make a bond with the hydrogen. Please remember this because I don't have space, so I need to erase it and then we come back to it later on. Do you follow me? Now the mechanism of the reaction. The first step, as we said before, H plus is electrophile. This here is like electron efficient system. Bi-electrons will be added, will be used to make a bond with the hydrogen. So therefore we will have carbon, carbon, H, and then this carbon will be a positive charge, carbocation. So this will be the slow step. The second step then, when we have the Br minus inside the solution, very obvious, the Br minus will attack plus, and then we will get the addition product. That's actually the mechanism of any polar reaction. Always this is true. Always true. First step, the electrophilic part of the adding molecule will add itself to the carbon double bond carbon and then forming a carbocation. The second step, the nucleophilic part of the adding molecule will add itself to the plus and making the addition product. Is that clear so far, guys? Alright, so this is actually what we call it, this is the general mechanism of any addition molecule. Remember that all the time. I will just rewrite it now in a generalized way. In other words, whenever we have carbon double bond carbon, the first step, what will be electrophilic part, the electrophile, the electropositive part of the adding molecule will react first and then make a bond with this bi bond and then form, it will form a carbocation intermediate in this case. So this is electrophile. Now always any electrophile in the system will never be alone. There is always its nucleophilic part. So there is a nucleophile. There is the negative part. The negative part then will add itself in here, and then we are going to get the adding molecule. Do you follow me? So always, oops, what's happened here? Do you see me, guys? Can you see me? Can you hear me? Okay,
Yes,
perfect.
doctor.
Sure. Okay. So this is actually, because look here, in the next chapter, when we finish this chapter and then we study the next chapter, there are plenty of mechanisms. I don't want you to be lost and to rely on memorization. I just want you to understand a simple principle idea. Every polar addition reaction this is the mechanism of any polar addition reaction to the carbon double bond carbon. Always, electrophilic part first of the adding molecule will react with the carbon double bond carbon, will form a carbocation intermediate like in this case, and then followed by the reaction of the nucleophile will act there. Do you follow me? Now, the question is, which I'm going to stop the lecture about it, the question is, what if we have a carbon double bond carbon system, alkene system, where it is not symmetrical? For example, hydrogen, hydrogen, here we have CH3, CH3. Now, and it will react with addition reaction. So it will be reacting with electrophile. The question is, where the electrophile should attack? Should it attack this carbon and forming the plus on that carbon, or vice versa? Should it attack this carbon and forming the plus on that carbon? In other words, there is two possibilities for the electrophile to attack or to react with unsymmetrical alkene like this. I'm going to write the two options. either the electrophile attack the first carbon, here for example, and then the plus in here, or the electrophile attack the other carbon and the plus will be there. So we do have two possibilities for the formation of the carbocation if we have unsymmetrical alkene. Which of the two will be favored? Formation of the first carbocation or formation of the second carbocation, and why? Based on what we have just studied a few minutes ago. Which is more stable carbocation? The first carbocation or the second carbocation?
The second.
Looks like many of you are answering at the same time, so I cannot hear. Which one is more stable carbocation? The first carbocation or the second carbocation? Based on what we have just studied a few minutes ago. Nobody is answering now?
The second one.
Why the second one? Why the second one? It's actually the first.
I'm not sure.
No, it's okay. The first one is more stable. As we said, the carbocation which is attached to more alkyl groups will be more stable. As we said always, whenever we have a process, the process will always prefer the more stable situation. And in this case, as you can see here, in this case, this is more stable carbocation because simply this is what we call it a tertiary carbocation. It is tertiary carbocation, but in here in the second case we have a primary carbocation, and as we have just explained in the previous slide, tertiary carbocation is more stable than secondary, secondary is more stable than primary, and primary is more stable than a methyl carbocation. Is that clear, guys? I just wanted to connect things together in order not to instead of simply studying things separately. Is there any questions so far? Is there any question? Inshallah, Ahmed, but actually you have to imagine, Ahmed is asking to upload the lecture directly on the YouTube. It will takes time actually. It takes time until I upload it from the mobile phone to my PC, and then from the PC to the YouTube. It's not just a matter of few seconds. It takes time, sometimes hours. So bear with me, Ahmed. Inshallah, by tonight you will see both lectures in the YouTube. Is that fine? The previous lecture is already there. So the Monday lecture, previous lecture is already on the YouTube. So always, you can simply subscribe to my YouTube channel. Whenever I upload something, it will appear right away, or it will simply give you a hint right away to your mobile phone. So you can always follow up any upload. If I forgot to inform you about the uploading of the lecture, you have it already. There will be like something to remind you about it. Haytham is asking which one is more stable, in other words. Which one is more stable, the cis or trans? Which one is more stable, cis or trans alkene, Haytham? Why type? Why type trans is more stable? Type why trans is, and Haytham, why trans is more stable? Why, guys? Why trans is more stable?
Because we are following.
Because?
They are far away from each other. So
which means less repulsion forces.
no repulsion force.
Which means less repulsion forces. That's it. That's why it's more stable. All right. Anyway, it's enough for today. Next Wednesday, inshallah, we'll continue every aspect about chapter 7, and then inshallah we may have even some time to at least start up discussing parts or some aspects of chapter 8. All right. Thank you very much again for your attendance. Yes, there will be actually. We need actually, because we are a little bit, we lost some time actually in the lectures. So we will definitely use the next lecture on next Wednesday in Wednesday lab. All right? Okay, I wish you a very nice day, and thank you for attendance, guys. Thank you. Have a